So we are talking about LC history, instrumentation in a common detector. Okay, so this is a black box, and they call it an HPLC. And hopefully by the end of the hour, it won't be such a black box anymore. But what does that probably stand for? Melissa, what does that probably stand for? LC is liquid chromatography, and the H is high. You would think high pressure liquid chromatography makes the most sense, right? It really does, but it doesn't sell as well as the P that these guys picked. I mean, look at the applications of this thing. You can separate mixtures and identify the mixtures. You can quantify, you can purify things. This is really powerful and really useful stuff. So there's a lot of money in it. So high pressure, yeah. High performance. So that's what the P is for, high performance liquid chromatography. So there's a lot of things you can do with this. Think of you can monitor, see if something's stable over time. Pesticide levels in the environment. I'm just picking out some of these. I look for somebody's narcotics, right? Synthesize some compounds, see how pure they are. Isolate compounds. There's a lot you can do. Okay. Are any of those uses, do they look like they could be duplicative, Jackie, of GC? We have this other black box with gas chromatography. You have some idea how it works, but does it look like any of those could be duplicative of GC? Or all of them? What do you think? It might be easier to say all of them. Can you say all of them? Right, because they're all chromatography. And anyone, look on that list, and there are some there you cannot do on the GC. Where's water pollutants? Analyzing water pollutants? Well, you could do that on the GC or the LC. You could analyze for water pollutants. In fact, use the FID on the GC, because then you're not going to have any background at all. And on the LC, no problem. I'm thinking of GC. Which one could you not do on the GC? Who's that instrumental here? Someone's had instrumental. Ricardo. Pressure is on, man. I have not written this letter of recommendation yet. What do you see on this list where, you can't do that on the GC. I lost it. I got to find it again. Oh, there it is. Because think of what I think of when I think of this. Here's the HPLC, and what's coming out of it? You have this little tube, right? And drip, 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 the pure stuff. You have a black box called the GC. What's coming out of the tube on that? A gas, a vapor, right? Yeah, again, it's going to be pure and things, but it's going to be a vapor, and very often your detector is going to destroy the stuff, right? Look at FID, it burns it up. So what I'm looking at is this isolating natural products, right? We have a scorpion poster over there, and it's outside the wall, just on the other side of this wall, and they're not so sure why scorpions glow in the dark, fluoresce, right? That's how they find them. They show them the little UV lights and they find them. They're not sure. Biologists, when I say the biologists aren't sure whether it's just a byproduct of their cuticle formation or if it's actually helps them. You know, the little moon shines on, and then the other little scorpions can see each other and do their little thing at night, right? So that was the idea of the research, is just to purify these things. And essentially, we had to use the HPLC, right? You grind up the scorpion dust. It's a story how this lady did it, but it was, anyway, we got it done, and then we extracted it, put it on the HPLC, and just had to wait for the right, just had little test tubes at the end, and collected all the different fractions, and put each one in a fluorimeter to see which one actually glue in the dark, or shine a little UV light on each little test tube, each little collection. So that's the power of HPLC. You couldn't do that on the GC. So that's what I see, is something that you couldn't do. Okay. Modern liquid chromatography all started around 1906 with a guy by the name of, I've always pronounced this Sweat, and I'm going to keep pronouncing it Sweat until someone corrects me, because I don't know how else it would be pronounced. Sweat, okay, now first you have to know what he did. Okay, he's the guy, I think I told you this story, he's the guy who's walking around in nature and sees all the different colors of leaves on the same tree. So he sees, well, man, all those colors must be in the leaves. So at the time, they had some chemistry going on, so they had petroleum ether, and he sticks all the leaves in there, gets all this black juice out, throws it on the top of a tube like this, okay, and throws all his extract in there, and then the stuff just dribbled out, and he got all the different little chlorophylls out of there. Now, he used chalk. Chalk. Ground up chalk is the stationary phase. Now, ground up chalk, what is ground up chalk? What is chalk? Monica, what's chalk? Calcium, starts with a C. Calcium, carbonate. Calcium carbonate. Okay. So how would you classify calcium carbonate, Danielle, on the polarity scale? Right? Of all the chemicals known to man, where would calcium carbonate fall? Polar. Little polar or extremely polar? Extreme. Because of that calcium ions and carbonate anions, you can't get much more polar than that. So this is a very extremely polar substance. So since historically he's the guy who started this all out, whenever you use a stationary phase in liquid chromatography, Marlena, that's polar, you're supposed to refer to that as blank phase chromatography. Normal. Yep. We never do normal phase chromatography anymore, but that's how it is. So later in the 60s, these LCs came out. So liquid chromatographs. What could be done to Sweat's system here? This is Sweat's system. Just imagine it. He's got this ground up chalk in here. Here's the chalk, right? And what could be done to turn this into an HPLC? Ricardo, what could be done? Since you're the only instrumental guy.
You would need a column.
Well, he's got the column. Check.
He's got the column. Oh, you need a detector.
Oh, he's got the detector, his eyeball.
The detector.
Check.
Computer.
Yeah, his eyeball can see the different colors.
How about different solvents?
He could change the solvent.
Okay.
Check.
Change the solvent. Okay. That's cool.
'Cause he's doing chromatography.
But what makes it high performance?
Yes, exactly.
Oh,
That's.
put a balloon on top of something?
Ooh, okay. Put some pressure on the top. Exactly. Put some pressure on the top. A balloon was a great idea. I like that idea. How do you draw a balloon? All right. And you'd have to keep refilling the balloon, but no big deal. You pop it off, blow it up again, right? Because you're just forcing the stuff through. Then all of a sudden, it's high pressure chromatography. No, you're not supposed to. They like high performance, but pressure makes a lot more sense because that's what it is. Okay. Of all known organic compounds, only blank % can be analyzed using GC. Let's see how good your memory is. No one else has taken this, right?
20.
Ooh, that's really good. See that? You just keep them going here. Okay. LC manufacturers spend a lot of resources to make their liquid chromatographs ultra low volume. Okay, so this whole black box on the HPLC, tenths or hundredths of a microliter is all it takes to fill up all the little tubings and things. So that's ultra low volume. Now they do that to minimize blank blank. They use it to minimize diffusion, but there are two types of diffusion, eddy and longitudinal. But I think we called it, I don't remember this. Did we call it zone? Maybe we didn't. Broadening, didn't we? Yeah. We did call it zone broadening. Yeah, so to minimize zone broadening. That's the best way to say it. I mean, the answer is really diffusion, but it's confusing because there's two types of diffusion, so that's why you say zone broadening. What is the difference between isocratic and gradient elution? So doesn't matter what the chromatography is, Sabina, you can do gradient elutions or you can do isocratic elutions. We had I think on the very first day, we had I had some water here and some paper filters, right? And then I had these colors. Remember that sitting here, and the water's being pulled up the paper and it was separating out the little vis-a-vis inks. Okay. Was that an isocratic or a gradient elution? It's isocratic. Why is it isocratic? Iso means what? One. Gradient means different step, more than one something. So isocratic means you're not changing anything. It's one step. Once you set it all up, you don't touch anything. So this would be an isocratic run if you go back and remember that, because we didn't change anything. We could have made it gradient by, okay, Andy, I want you to, after this has started in 2 minutes, I want you to dump some ethanol in with the water. Okay, and then Kelly, in 5 minutes, I want you to heat it up, right? And then see how you can change all these different little things? You change anything. Change at least one thing, then it's called a gradient elution. So that's the difference. But it's a big deal because that's the chromatography. Chromatography, thinking it as in terms of a verb. How do you do chromatography? We're going to do chromatography. Well, you do it by doing these gradient elutions. Okay, great. Well, what can you change in liquid chromatography? The solvents, which aren't pictured in this black box. Oh yeah, they are. Here's our solvents. And then all those solvents, you can kind of see the little tubes coming out. They're going to a valve, and it can suck out different proportions. So at the push of a button, or the computer you can set it up, it can pull out it can change the composition of the mobile phase on the run. And that's how you do chromatography with HPLC. That's how you do gradient runs. That's how you do the separation. You could go through all the work at changing columns and things, but that's really going to slow you down. It's not very...
Temperature on HPLC too, right?
Yes. Yeah, they have this thing in a big oven.
But is it more common to do...
And it doesn't really help. I think changing temperature doesn't really help so much. What it does is just makes things look prettier, which is kind of nice, right? If this is your business, or you want to lab X analyzes the narcotics in someone's urine and lab Y analyzes the narcotics in the same urine, and then you take a look at the two. Ooh, this one looks prettier. Yeah, so I think it just sharpens up peaks is all the temperature does for LC. So this one, exactly. Kimberly's exactly right. Change the mobile phase composition, right? Change those solvents. In GC, though, what do you change? The temperature. Exactly, because that whole column in GC, that capillary column, was contained in an oven. So you change temperature. Very good. Now there's other things you could do. You could change flow rates. You can change temperature of the column in LC. But the most common is what we mentioned. Mobile phase composition for LC and temperature for GC. Okay. So inside that black box, here's the flow diagram of how things are working in a liquid chromatograph. So the only one I labeled is a computer, and then it all ends up in the waste, right? So I guess it ends up in the waste. Okay. Well, before it goes into the waste, what's the last thing it must enter? The detector. Good. So the computer, just do electrical connections as dashes maybe. And so the computer's got to be connected to that. Okay. So let's start at the very beginning here. Okay. It's kind of similar to the picture. These four rectangles are probably what? Just different mobile phases, different solvents. And you can have like pure solvents in each one, or you could have a mixture in them. You can put whatever you want in there, right? So here's our solvents, our mobile phase. So we need to have these guys going to little valve kind of thing. Okay. So we want to be able to pull out different proportions of different solvents. Maybe 100% of one, or maybe 50% of the other, or change the percent over time. So all of that is with a solvent proportioning valve. Proportioning valve. Okay, so that better be hooked up to the computer. Okay. Then it's going to have to go to probably what? What would you guess? Jeffrey, you have a guess? Something's got to be sucking this stuff out of there. Column's going to be further down. Something has to be sucking this stuff out. A vacuum or a pump or something. And all they're going to, right now, again, it's odd that we can put guys on the moon, but we can't think of anything different than this to push liquid through, right? So Marlena's where I want it to end up. So it pushes through, right? Then it sucks it up, and then it comes back, sucks some more up, and pushes it through. It has this double piston thing going with little valves in between. But the point is that's your pump. And it's pretty high pressure. We're talking hundreds of, you can get 300 psi easy. So that's where solid line, because they're connected, right? Once this guy mixes it, okay, and then the pump is pushing it all through, sucking it up that way. Now I guess it's pushing it, okay. And then what's kind of odd, what would you call this? Maybe a pressure dampener. And I think this is just evolution, because guys, before they would get this, without this, they'd have their time and their signal, their chromatograms, and it might look kind of like this. Little pulse ripples, instead of looking nice and purty, right? Let's get rid of those ripples, because it's pressure ripples. When you really got to zoom up to see it. But so that's why they have a pulse dampener. Okay, that's what that is. Okay. So here's the column. Well, they don't just call it a column. It's an analytical column. Probably they throw that word analytical on there. That way they can justify the price. It's like $400 or $500 for one of them. But they are pretty special, and we'll talk about that later. But so somewhere in here, though, you have to, what? What are we missing? Well, that's kind of what the analytical column is. I mean, it's, yeah, you got to, somehow you got to introduce your sample, your analyte. Somewhere you got to inject this stuff. So now it's injected after the pulse dampener. And you can have, there's all these different types where you can, suck it up with a syringe and just manually inject it, or like what we have, you push a button, and right? You have this auto injector, set it all up, and you can go home and do all your runs. We forgot about our electrical connections. Right? That pump better be connected to the computer. Pulse dampener had better be connected to the computer. The injector better be connected to the computer, so you know when it's injected, so then you know when time 0 is. Okay. So this analytical column, if it's around $400, you're going to want to protect it. So you buy a little dinky, tiny analytical column for a fraction of the price, like $40. And they call it a guard column, what Ricky mentioned. So that's before it. Not absolutely necessary. In fact, we don't even have one upstairs because we ran out of money. Not the $40. They want close to $1,000 for the little container that holds the $40 filter. So we don't have the 1,000. But okay. So now see how guard column, analytical column, no electrical connections. This is where the chromatography is being done. This is where the stationary phase is. Okay. And then it goes on to your detector, and you get your chromatograms. Okay. So out of the computer, right, and you get your chromatograms. You know, time and signal on your little computer screen. So a common detector, the diode array detector. Now I was thinking about, no one's probably brought their calculator, because the ones that I borrowed out all have those little solar cells on them. So I was thinking, okay, I line you up here, everyone's holding their own little solar cell. And then we make a diode array detector. So what we're going to do is, someone's going to be the, right, I have to almost draw some squares here since I don't have anybody. Right, so you have your little solar cells on there. So there's my diode array detector. So I have kind of like the red is on the most furthest on the right, and the green looks like it's detecting green furthest on the left, right? So all this is fixed. It's not jiggling around or anything. This is a fixed thing. It's measuring all wavelengths at the same time. And then your sample is just going in between here. So if it absorbs red, well, then a little bit of the red's going to be attenuated, and that solar cell would detect it. But they don't call them solar cells. They call them diodes. And then if you have a bunch of them lined up, they don't call it lined up. They call it starts with an A, array. Right? So diode array instead of a whole bunch of solar cells lined up. So, see how it sells? These guys know how to make money. Okay? So and that's pretty much all that's going on. Partition chromatography. So this is what life has evolved to in HPLC right now. The most common type of liquid chromatography performed is bonded phase. So all they're saying is oh, and I didn't bring a column. Do I have time to go get one? Yeah, I have time to go get one. I think I have time to go get one. Let me go get one. So just to pass some of the stuff around, you'd have to have scanning tunneling microscopy to actually see these particles. But see how they're roughly spherical. And they're just essentially glass beads, extremely small though. But at that, like on the order of 5 microns, 5 × 10⁻⁶ meters, I'd say like 10 times the width of a hair, so somewhere around there is how small these beads are typically, like around 5 microns. So what they do is they coat these glass beads with the stationary phase. So what does it look like macroscopic wise? Here's one of those guard columns that's broken, and you can see that it just looks like a white powder, stationary phase. Or you can take one of these. Here's a column for liquid chromatography. See how much bigger it is than capillary columns, obviously. But you can take the end and you can unscrew it and take a look at that and see what's in there and see what it looks like. You can see what ultra low volume means because it's an extremely small size there. You'd never do that to, in fact, you'd never even do this to an analytical column because now you just change the packing on the end. And then you're going to mess, it's not going to look near as nice as it did before. You mess with eddy diffusion then, for example. Anyway. Where are we? The most common type of liquid chromatography, in this type of chromatography, the stationary phase is chemically bonded to a, what would you like to call it? Glass bead? Right? But it's beads isn't a small enough word. A glass, really, really, really tiny ball. That's what it's bonded to. Okay, so what's glass? What elements are contained in glass? Like in the window? Silicon and a lot of oxygen. So you've got the silicon oxygen thing going on here, right? So I'm just drawing. But the point is over here, right? Okay, so does this look like here's a hunk of glass, right? And it's supposed to be somewhat round, but it's zoomed up so it's not so perfectly round. Does this look like a hydrophilic or hydrophobic surface? If you remember your terminology there. Hydrophilic, right? This attracts water big time, right? Glass, put water on glass. Yeah, it just spreads out. It doesn't do anything special. Okay, so what they're going to do is they're going to put the stationary phase, and it's a big patented secret in how they do this, but essentially we did it upstairs. It's not, anybody can really do it. You can't do it as well as these guys, though. That's really where the secret comes in. We'll show you why things are getting short-combed. But when they say, I don't know, that thing that's being passed around, I think it says ODS on it. And it might also say 5 micron on it, on that column that's being passed around. So those beads are about 5 microns in size, if that's what it says on that. ODS is octadecal silane. Octadecal is how many carbons? C18. So what you have to do, what you have to do is replace these H's with 18 carbon, an 18 carbon chain, right? So let's replace all of them except for that center one. We've got a lot of C's to write. Oh, what we could do is do parenthesis thing, right? 4, 14, huh? Can cheat. So you just have a big long carbon chain. I got 3, so I've got 15 there. Well, heck, let's just write C14. Oh. And you have to put all your H's and stuff in there, but I think you got the idea, right? Oh, I did it on the wrong one, right? Our patented process gets us there. Okay, so they try to coat this entire particle with these long chains, or whatever you want to coat it with.
C18.
C18. Okay, and it's really CH2, 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 right? And then your last C is CH3. But they can't cover them all. So this is what ends up with this peak tailing. These uncovered hydroxyls. And all that is you can't even really tell because they've gotten so good at this. But if you drew a perfectly symmetric peak, it might look something like this. But a peak tailing, just try to draw the tail a little bit longer on one side than the other. Right? That's tailing, either one way or the other. Okay. So it's not a pretty peak. And it's also, notice, the wider it is, the harder it is to resolve different components. A blank stationary phase is referred to as reversed phase chromatography. You'd probably guess which one, if you recall what normal was. If normal was polar, reversed is probably going to be nonpolar. So there's some things that you're not supposed to do in LC. Okay, but we have about 4 minutes left. I'll filter all the samples demo. That's kind of a boring demonstration. All you do is just suck stuff up. All right, suck it up, shove it through a little filter. Okay, everything needs to be filtered before you put it on the LC. Benzene's injected on a C18 column. You don't change anything but the column. Sketch how these chromatograms would look. So let's say C18, it looks like this. One peak is just one component, and let's say it comes out at 5 minutes. Well, you put it on a C8 column, so you understand where the C18 and C8's coming from? On those little glass beads, they just coated it with less carbons. So if you coat it with less carbons, that's the only thing you change. Would benzene elute faster, slower, or at the same time? And this is where it gets odd, I think. This is where the thinking of a chromatographer comes in, this idea of organicness, right? Benzene is a very organic or inorganic compound. Very organic, right? It's all C's and H's. In fact, it's even aromatic. So then, which is more organic, C18 or C8? C18 is more organic. Okay, well, like dissolves like. So benzene will have a higher affinity for C18 or C8. C18 has a higher affinity. It's retained longer, right? It's retained better. So that means it should come out what with C8? Come out faster. Longer would mean that it's retained even better. But it can't be retained even better. It has to be retained worse. So you have to draw a peak somewhere that's faster than 5 minutes. And it can't be retained the same because it's a different stationary phase. So the retention, the like dissolves like, is different. So here's my 5, there's my peak. Okay. So here's a HPLC run. And they're saying they use 45% ethanol, 55% water. So it's an isocratic run. They didn't change anything. They left it at these settings right when they click start. And there's your result. Well, you've got these late eluters. Okay. But these guys up before 5 minutes are all pretty nice. I wouldn't really mess with those. But I mean, you could tell the computer probably, hey, after 5 minutes, change the mobile phase to what? Now, there's a couple of things you have to think of to answer the question before you spit one out. One is it's a C18 column. So are you doing normal phase or reverse phase chromatography? It's C18, so you're doing nonpolar, which is reverse. So you're doing reverse. So this, I don't know if that helps you. Or just think of it as you've got a really organic column. So what's going through is ethanol and water. So the guy who's eluted last, you want him to speed up more. So this guy that's eluted last, he's very organic or very inorganic? He's very organic, right? So that's the thinking you have to realize. Reverse phase chromatography, last eluter, most organic. Okay, I want this last eluter to elute faster. So at 5 minutes, since this is all okay, I'm going to change this mobile phase composition to what? You could make it all ethanol. You couldn't get it more organic than that, right? You don't know, you just try it. But that's the direction you got to go. You up the ethanol, down the water, right? So 85% ethanol, 100% ethanol, whatever. Just pick a number that's bigger than 45% and try it. Okay. So this can be part of the homework. Just write GC, LC, or both next to each one. And then add that to the homework since we're kind of out of time. I don't know. We have this to do. Are we done already? There's no, this is the last day? There's no day 30?
Yeah, there is, but.
We'll do day 40 then. You'll get by. Well, probably, it could be on the final.
Are we taking a quiz next time we come in here? Yes?